Okay, hello. Good afternoon. My name is Jung-Shin. I will share my experience during last 6 months to train 100 billion model from scratch with more than 500 Blackwell GPUs. So why we build from scratch? There are many open models, but there are many requirements to build from scratch sovereign AI models. Because model is not only used by single personal or the enterprise, but also used for the defense and privacy, security constrained environment. So more and more nations, companies are trying to build their own AI model. So the Korean government also tried to build their own sovereign AI model. So they just picked the 5 teams among the whole South Korean startups and enterprise. So we were one of the consortium to build our own sovereign AI model. But the problem is that as the size of the infrastructure grows, the number of errors also grows. So failures are inevitable in the situation. So this presentation is more about our failure record. Of course, we had a successful training with just less than 3 months. However, we had a lot of troubles during training. So this is our AI cluster. We are using the SK Telecom's Hain data center. On top of that, we use the fast data as an ultra-fast storage and the NVIDIA GPU, especially the Blackwell HGX, as a training node. And on top of that, we use the backend AI, our own orchestrating platform. And also, Offstage is making their own sovereign AI model on top of the backend AI. So it's a very well-known configurations with local and InfiniBand network and that's data and request storage. But it's very rare to Kubevert as a virtual cluster solution. So we just built the entire setup on Kubevert. So we could achieve the same API with Kubernetes, but we could use the VMs. And also we use the PyTorch, but the problem is that the Blackwell architecture is very different from the consumer level and the enterprise level GPUs. So the ecosystem is not well cooked yet. So we had to use the monkey patch, the PyTorch version, and also we had to use the Torch Titan, it's an early stage distributed training framework. So we had a lot of trouble with that kind of setup, but it's getting better and better. So what is backend AI? It's a software-defined AI infrastructure. So backend AI just orchestrate, schedule every single workload on top of the infrastructure layer. It can be the CPU or GPU and other NPUs like a group card. And we are making the orchestration layer. So we have to solve every trouble from infrastructure layer and also from the framework layer. So we just made a Sokoban scheduler that's the orchestrating solution, not based on Kubernetes. It's our own scheduler, but it has a compatibility with the Kubernetes API. And also on top of that, we use the Fast Track, it's our MLOps platform, to achieve the auto recovery feature because every failure follows the restarting or continuing the training job. So we received the 63 Blackwell nodes, and we just reserved the 3 nodes for the troubleshooting. So usually we use the 480 Blackwell GPUs to train, and 3 nodes are reserved for changing the hardware, but usually they were used to generate the synthetic data. So if the main cluster has a trouble, we just pull out the hardware and change it from the reserved path by stopping the synthetic data generation. So we found very interesting situations. For example, we had more than 200 training sessions, but just three training nodes had made more than half of the trouble. That means that the trouble itself is inevitable, but always there are troublemakers among the whole entire cluster. So only top 3 nodes caused 50% of every troubles. And during the recovery stage, we had to restart the training from the checkpoint, and it took 2.6 seconds, and we reduced the recovery time by 47%. And actually, this kind of a record is already shared by Meta and ByteDance. But we found that there are many differences between their report and our result. For example, the ByteDance just shared that most errors are from the NVIDIA. But in our case, our troubles are mostly from the ECC and PCI downgrade. So why this happens? Because our palm is much smaller than the ByteDance or Meta's. They are using more than 10,000 GPUs, but we are just using the 500 GPUs. So the number of NVIDIA hardware are much less than the bigger palm. So the trouble pattern is very different. So it means that we need to care about the size and trouble point among the palm size and palm architecture. And to gather the data, we just made a OSMI. This is open source monitoring platform, open source monitoring software to record everything from your GPU or your chassis or your cluster. So we just monitored every metric from every node. But we also use a DCGM and node exporter and also the backend.ai native metric to compare between the metrics. So we just recorded more than 300 metrics real time from entire training process. So we found that this is a session life cycle, and we found that if GPU has a trouble, of course we can change it. But the best way is let's just predict the GPU, whether the GPU will have a trouble or not. So we try to find a way to I don't think it's a good idea, but anyway, the Minority Report, the movie. So we need to find a GPU node who will die. He will die. So we just measured every metrics and compare with the cross-domain detections. So usually the GPU failures are followed after the scheduler metrics because the scheduler has some tail latency and very slow orchestration response or others, especially for the number of the tasks of each training node. So if the async task count is increasing, maybe in a short time, the GPU will have a trouble. So we can find a precursor. We could find the precursors to find future failure GPUs. So it's better to have a wide net. So more metric will save you and prevent you from unexpected node down. So what is the difference? Because if we know when GPU dies, we can save the checkpoint before some specific node dies. So it will help us a lot to save the training time. And also there are many troubles. I don't have enough time, so I will just summarize. One is the storage I/O, because when we just made pre-testing farm with four nodes, there was no trouble. But if we just increase the number of the nodes up to 60, the IOPS just spiked, and it's more than our expectation, up to 80 times. So we need to find a way, reason why. So us and Upstage model company and the SKT, the cloud company, and the NVIDIA and past just dig into the issues to solve that. And we found that it's the result of many problems. For example, NFS driver had an issue. NFS driver just split the 2 megabyte packet into 4 kilobyte packets. So it just make a lot of IOPS. It's more like attack from the training node to the storage node. So with that, we also apply the file level error sharding and async deletion, and we read ahead tuning. So all combined with that, we could reduce the starting time from 8 hours to under 8 minutes. So, and also we could solve some training scheme. For example, if we change the router D-time mismatch after sigmoid, by changing the Hopper optimized parameters into Blackwell optimized parameters, especially for the GMM, we could achieve the speed ups. So it's very important to understand the difference from the Hopper and Blackwell. And between Blackwell, there are consumer Blackwells and the enterprise Blackwells. Their compute capability is very different. One is just 100 and one is the 120, right? And also there are many troubles from the NCCL. The nickel has some bug always. So we needed to find a bug and we had to fix it with NVIDIA. So NVIDIA just released 2 more releases during our training by founding from our training farm. And also we had to tune the network because we are using not only for the InfiniBand but also local and management network separately. And by combining them, they always make some troubles, especially from the PCI Express tray. So GPU failures are not only from GPUs. Actually, it's a combination of hardware, software, network, storage, and other stuff. Because the complexity always grows nowadays, and the GPU palm, the GPU training cluster, is too complex to understand by just one side. And we could reduce the recovery time, and we could for failure waste time, and we could change the checkpoint optimization by finding some rules from the data and pre-saving the checkpoint before the trouble. And of course, failures are not uniform. It's more like a random, but it's not random. Actually, we can predict. So by last 3 months, we learned that the failure taxonomy, and there are many kinds of metrics, but it can be different from one cluster to another. And also system stack is also affected to the training and the software running and the compatibility too. And to solve that kind of problem, every companies from the infrastructure, software, storage, network, even the modeling company should collaborate to optimize. As a result, we could make the 100 billion from scratch model less in just 2.5 months with only 500 GPUs. So yeah, large scale training is it's a normal state, it's a faulty state. Usually at the high performance computing era, we believe that the normal state, healthy is the normal state, and the failure state is abnormal. But with GPU era, we have to change our mind. The trouble state is a new normal, and the healthy state is very rare. So we need to re-architecture every software stack to change our baseline from the just a clean state to very dirt, but unstable, but manageable state. And the scaling test is very important before starting your large-scale training. And also cross-organization and transparency is very important. That's why we submit this presentation to yours. We also made a very detailed report about what we experienced during last 3 months. So our booth is there to post 3, and if you have more questions, please visit our booth and enjoy and share your opinion and give your question to us. Thank you for listening.
Thank you for joining this session.